Welcome to my talk on using non-C languages with Zephyr. No button, no automatic advance. Just a little background about who I am. I'm David Brown, D3Z on GitHub and Twitter and other places. Ask me afterwards if you care about the story behind that. I've been part of Linaro for a little more than 6 years, part of Linaro's Internet of Things and embedded team for about 5 years. I'm a maintainer for the MCU boot project, which is a bootloader that's kind of the bootloader you get by default with Zephyr. I've been the security architect, or was the security architect on the Zephyr project for about 2 years. Most of my career focus has been on security. I'm also a reviewer on the Embed TLS project and some other security-related things. I'm also a jazz pianist. That's not really related to the talk, but people do ask. So we're at the Zephyr Dev Summit. I'm not going to give you a background of what Zephyr is, because that would hopefully be redundant. But if you've looked at Zephyr, if you studied it, it's a bunch of C code with a smattering of assembly. There's a lot of Python code and CMake and this kind of stuff in there, but that's all the stuff that runs at build time, and it's the C code and the assembly that gets built into this application that you build. We have a very complex and rich build system. We've got kconfig, there's device tree, CMake, and this is great. I mean, this makes Zephyr really nice to use because you can just go configure things. You can change something in you have an override project config, and now you have new features in your code and that kind of thing. So how do you build a Zephyr app? I mean, this is a really basic, this is my supposedly not talking about Zephyr. You go run west in it, it gives you this big tree with the Zephyr tree and a whole bunch of modules, and then you put your app in some other directory, and you basically write 4 lines of CMake pointing it to your source file, and the Zephyr build system just takes care of all of this. You get a thing that can then be flashed onto your target. But the big thing is it's in charge, and it does the configuration. It compiles things. It figures out like what boards and devices and stuff are available. Builds all kinds of tables at runtime, at compile time, and syscalls and macros and stuff. Links the whole thing together, and you get something that runs. And for the most part, that's really nice, except it's kind of annoying for the topic of my talk here. We start to get into non-secure languages. So before we get into the details, why would you want to use a language other than C? It's getting to where I don't know that I need to really convince people that this is the case anymore. There's a lot of things, safety, security, robustness, kinds of things, pointers, array safety. It still baffles me that we're using a language that doesn't check array bounds. That's probably the most common exploited security vulnerability are buffer overflows. And we are in the security committee discussing a replacement for the C library for the functions that do string manipulation because they're length-based and don't care about how big the buffers are. And the replacements aren't any better because you then have to manually pass these lengths around. And all these other languages, their idea of an array has a length that goes with it. And the language checks that. And you don't get that. And of course, the most important reason to use a language other than C is fun. If you haven't gotten into any of these other languages, there's actually a lot of, there's a challenge to learning them. And then you realize, wow, the language is helping me. It's not getting in my way. This is kind of cool. And then another one is available software. This is usually given as the reason why we need to use C, because there's some library that I have in C, and maybe C++, but we're starting to see more code in some of these other languages that we can then, how do we integrate that? How do we use that? So what I'm focused here is not really C++, and not because, oh no, C++ is bad, but because people were doing C++. If you were here 10 minutes ago, there was a whole project built around that. And I'm also not really here to talk about Python and JavaScript and Lua and some other kind of these interpreted languages, which people do this on Zephyr. But my focus here is low-level languages, things that compile to native code, small runtime, probably specifically not having a garbage collector, things that can be deterministic. So we're going to talk about three languages. There's one you care about, one you don't, and which is not COBOL, and then one you probably haven't heard of. So what are they? The first one's Rust. That should probably be obvious if I'm wearing the t-shirt. This is really busy. There's a lot of people talking about Rust. A lot of people talking about Rust on embedded. There's some work on Rust for embedded, but their focus mostly is on standalone, where you build a Rust program and then you link in the HAL right into your program and it builds the executable with no RTOS. And if you've ever done this, there's definitely applications for it, but it's challenging. All that stuff that the Zephyr build system takes care of for you, you get to kind of do that in main and point to the, oh, it's like, this is my board, I'm going to initialize this hardware, and that kind of thing. And the big thing with Rust is this thing called pointer safety through borrow checking, which I'll cover in a minute. The second language, the one you probably didn't know about, is Zig. And it's it's newer. It's not at 1.0 yet, so it's still changing. It's a bit simpler than Rust. Still has checked arrays and pointer safety. But the reason I found it interesting is because they have a bit lower level of a focus than Rust. They're really kind of targeting being a C-like language, but fixing some of these things. Then we have Ada, which that's the one you don't care about. But everybody's heard of this. This language was kind of created for this embedded kind of space that we're in. As I said, I'm not joking, but only sort of. It's very mature. This 95, 2012, 2015, 2018. There's a couple of revisions to the standard. It's actually active. Well, as I run into a company that wants to sell me tools to work with this, and it's probably not really relevant, but there's some things to learn because of the history the language has. So what is exciting about Rust? So real goal here is to have complete pointer safety. I mean complete pointer safety. If you don't use the unsafe keyword in your code, there will be no null pointers. There will be no use after free. The most common way to handle this in modern programming languages is to garbage collect. Your pointers are always valid because they don't go away until the runtime can prove that they're not used. GC garbage collection has issues, though, in embedded systems. I mean, we often are trying to not allocate at all, let alone having a garbage collector free things that maybe, based on whether they're used. So the way Rust does this is it has a concept of ownership, that every pointer in the system has one in exactly one place in the code that owns that. And it may be a variable in your code, it may be a field in a struct that's owned by someone else. And that can be moved around, and then they can be loaned out. And the compiler basically proves that those loans, the borrowing of those pointers, can never outlive the ownership of the pointer. And it's a kind of a bit of a concept to wrap your head around. It is the most difficult aspect of Rust to learn. And say you program in it and you're like, wow, that doesn't work. How do I make this code compile? How do I get this code to compile? You do that for 6 months, and then suddenly you just write code and it's no big deal. And then it affects how you write code when you write it in C and C++ and other languages. So, and there's reference counting for the case, because it basically requires your data to be a tree, no links back. And so then there's reference counted other kinds of things for when your data really does point back, because real world data does do those other things. The main thing the Rust people figured out is this worked much better than they expected it to. They were thinking, oh, this will give us pointer safety. And it turns out that this actually helps out with memory safety across multiple threads. I've written code where I was going to share some variable and the compiler came back and said, well, that's not actually allowed. I wrapped it with a mutex and suddenly the type of the value allows me to pass a reference to something else that it didn't allow me before. So the idea is you get the best of both worlds. It's like writing in a garbage collected language where you don't think about allocation and deallocation, and yet it's all happening kind of deterministically. So Rust has a big ecosystem around it. Software is encapsulated into crates. I'm trying to make sure I watch time here. They solve the versioning hell problem that often happens with many things by basically isolating the namespace so that if somebody depends on regex 1.0, somebody depends on regex 1.5, you can actually just build that and both of them are brought in, and there's no conflicts with the names. That's actually kind of a problem for embedded, because if you're not careful, well, we just added a whole bunch of code to our system. So typically when you're writing Rust code, you just kind of, oh, I want that module, I want that crate, I want that crate, I want that crate. It takes a little bit more effort when you're writing embedded code in Rust. You do have to think about that. There's a very large, over 16 billion served for those old enough to remember the McDonald's signs. And so to a Rust developer, an ideal world would be that you just add Zephyr as a dependency in your cargo file saying, I depend on Zephyr. I'm not doing that here. That might be something that happens in the future, but remember we talked about how Zephyr wants to be in charge. The build system wants to build everything. So we can't really build that way. We'll get into how we actually do that. So let's look at Zig briefly. This one you probably haven't heard of as much. The idea is to be a simple language, no hidden control flow. So that means no automatic destructors, no magic blocks of code. So the whole thing, if you remember the C++, we had to go through and, well, how much code did this generate? The idea is, it's really obvious how much code gets generated from the constructs. It's just, if you don't call a function, no function gets called. But it provides some support to help you with that. There's this thing called defer, which says when this function exits, no matter how, always run this function, and that kind of thing. No hidden memory allocations, no preprocessor, no macros is the goal. But it's not just to be a boring language, because they added all this stuff about compile time, kind of like what const expr does in C++20. But the idea is that what you need to do with macros, what you need to do with, templates, I guess would be the closest equivalent, is doable in this language. That's yet also still a very low-level language. Practically, I mean, it's very early. I wouldn't design a product around this language at this point, because it's going to change before it's released. But there's a lot of really neat ideas in the language. They took things that seem similar, like structures and modules. Well, they're actually literally the same thing in the language. Functions, type templates, well, they're the same thing. Your functions can return types, which means they have to run at compile time. Some strong robustness ideas, the idea of option types, error handling, there's no null pointers. The allocator, if you do need one, like you want to have a dynamically allocated array, you have to pass the allocator into that, and they provide a bunch of them, and you can write your own or just point it to Zephyr. This language is probably easier to use in Zephyr, mainly because they're more focused on being able to interact with C and call C. So Ada, I'll go over this quickly. Ada had a lot of great ideas. There's a lot of stuff that they wanted to do in line, similar to what Rust is doing, but that was deemed too expensive to implement in a compiler. The idea of borrow checking and that kind of thing, probably it would have made compile time unbearable, and the compiler probably wouldn't have fit in memory. It's verbose, it's chatty, it's not a very pleasant language to program in unless you really like to type. And there are some great ideas, but I think Rust addresses a lot more of these now. If we're going to sit down, unless you've got some contractual obligation to use Ada, probably would want to focus on Rust instead or something else. But there's even some great ideas in there as far as real-time operating system scheduling that I don't see very much elsewhere. This thing called priority ceiling locking that makes for really simplistic management of coordination between threads without actually having to have mutexes and that kind of thing. So don't dismiss it completely. But so there's a URL to a GitHub repo. This might be handy, especially if you're following online and you can't see what I'm doing. This is all of the code that is going to be here is in here. This builds. The environment can be a little complex to set up. I have a shell.nix file. If you want to balance the trade-off of, well, should I install Nix or should I try to install all these dependencies? But that environment actually will build all of this stuff. So, brief overview. Rust builds with cargo. Cargo does everything, kind of like Zephyr's build system. There's a cargo.toml, which describes, well, basically what are my dependencies. And the code is in source. So, if we look here, we have cargo.toml, a source file. There's a main program that's really exciting. There's a cargo.toml file, which gets some basics about this crate that I'm creating here, and the dependencies, which I don't have any at this point. And if we do this, it builds it and it says hello world. Yay! So Zig compilation also is managed by the Zig tool. A little different module of each file is a separate module, and they can reference each other. They don't really have a concept of crates yet. And outside dependencies is on their to-do list for something to do. Hello is more complicated. Things like standard I/O and an allocator aren't assumed, so those have to be manually specified. Error handling is explicit, similar to Rust. And there's just a lot of really weird concepts to this language. So if we look at Zig, we have just a simple file here. And I'm not going to go into full details as to what all of this means, especially the weird stuff like this thing standard that I'm implementing is just a variable I'm defining. It happens to be a module. And I can get standard out and stick that in something, and I can print that out. And yeah, standard I/O, though it's calling functions, is run at compile time. So there's some kind of fun stuff with this language. But if we can build this, and then we can run it. It says hello world. I will stay here for a minute because it doesn't seem to like me switching. Ada is kind of weird. It's very chatty. With Ada text IO, use Ada text IO, and put line and hello world, and even weird things like the snake case variables with underscores is a convention. And yeah, did you? Oh, sure, I'll cover this. The question is, why is there a try in the Zig code? So, no, there are no exceptions in the language, but this was equivalent to the question mark in Rust. So this says, this thing returns an error, so we have to handle it. Try says, oh, this thing, if this returns an error, propagate that error from the function that we're in. And the return type of main has an exclamation point, which is the indicator that it's not returning a void, it's returning a result void, the equivalent. I don't know if anyone cares about the Ada program, but there it is. And the Ada one, read the slides if you care. I don't have that much time. So what's common about these languages? They all have their own build tool. I didn't actually build the Ada program, did I? Not all that exciting. So the thing that's common about these languages, they have their own build tool that really would like to make an executable. They're usually thinking about desktop environments with them. And this is in kind of direct conflict with what Zephyr's build system wants. Fortunately, they have this notion that I can build a library. And that's what we're going to do to make these all work inside of Zephyr. The language thinks, oh, I'm just going to make a library that somebody else could use. And lo and behold, now we just tell Zephyr, hey, just use this. It doesn't matter that all of our application is in this little external support project. So there's a hidden difficulty that comes up here. Zig and Rust are based around LLVM. It's a great tool for this. Zephyr pretty much builds with GCC. I tried to get Zephyr to build with just regular LLVM, and when you pound include just zephyr.h, you dive into some files that clearly have bit rotted. There's support for LLVM in there, but there's also like GCC specific stuff that got dropped in at some point, and it would need to get into CI and tested. So I didn't set out to fix that for this presentation. However, they're supposed to be ABI compatible. It's not that big of an issue. But there's this thing called libgcc and an equivalent on LLVM, and they don't always line up. Although I've been told that I need to talk to the LLVM people about that because they want this to be possible. But right now I have to have some workarounds for some of these functions that LLVM's compiler wants to call that aren't in libgcc, and if I pull in their whole support library, we get conflicting definitions. So, and then if you try floating point, you get about 40 of these, so I didn't go there. All right, man, we're not going to have time to go through much of the code, so it's all in that repo. How do we do hello world in Zephyr? So the idea is I want main in as a Rust program. I want the main to be called from it written in Rust. I do a CMake that adds the Rust code as an external dependency and a bunch of clumsy mechanisms to tell Rust to build this as a bare metal thing. And then some stuff about panic and error handling that you have to do in Rust because it wants to know what to do when everything goes haywire. And we don't have standard yet. And I'll get to that if I have time at the end. But Rust can call C functions. It's perfectly happy with this. You basically have to replicate the prototype of the function in Rust and map the types. So to give a basic example, we have this. This is the CMake gunk to pull Rust in. A vast majority of this basically says, oh, just go run cargo build target and release mode. And then the rest of it is just telling it where everything is because it assumes this is an external project. The cargo toml is pretty simple, but we do have a dependency on panic halt, which I mentioned. Kate? I did earlier, and now I need to remember how. Control plus works if you don't hit shift. How's that? All right, so there's some extra funny stuff in here to get the code to be reasonably sized and that kind of thing. And then the code itself is in here. I have some extern C blocks for some C code. Print K was the first one that I called, and I just tell it that it's a constant U8 pointer. And then I have some other things that I did. And then we have main, where we call hello from Rust, and I have to be explicit with the null unless you want it just printing garbage for the rest of memory. And from Rust, this is the most unpleasant aspect I've run into as far as interfacing between C and Rust, is that Rust doesn't use null terminated pointers. It keeps the length explicit, so you have to put the null in there. And for string stuff, that gets to be annoying. But I got this thing, I implemented a small logger implementation in Rust so that I can do log, and this comes out in Rust. Thing is, what do they call it? We called it main. So I actually did this wrapper. This isn't necessary. You can write main in Rust. It works fine. But I was trying to find out what was wrong when I was debugging all of this. But then I wrote this function here, which basically translates between the log levels in Rust and does one of the loggers in Zephyr. So I'll just show you this file. I'm just going to do a west build and a west run. And this takes longer because we're building a Zephyr application. We're not just building hello world. It apparently takes a lot longer when I'm not plugged in. So we're spending a very fractional amount of the time building the Rust application, but then we get log messages in Rust, and we have no peer. So guess what? We could do the same thing in Zig. We're going to make a library. We're going to cross-compile. We're going to do exactly the same thing with CMake, except with a Zig command. The Zig runtime requirements are less. It didn't require that panic or thing. They're kind of assuming you're a module. And, well, there's a neat thing that Zig has where you can say, oh, here's a C header file. I'd like to call those functions. And it violently fails in Zephyr right now. And that's because we don't support LLVM. As soon as it goes and tries to parse through kernel.h, it gets to these files and says, oh, you're on LLVM, okay, I'll bring this in, and then it doesn't actually work. So we don't get to see that. What we do see is we have our Zig main program, which just logs some messages, a couple things to set the logger up. We have a similar kind of, this is almost identical looking. The difference here is that in, where do I have the declaration? So this is actually not used. Zig is lazy. If you include something and you don't use it, it doesn't matter if it doesn't work, because it doesn't try to do it. But when we log message this really weird construct here of array *:0 thing, this tells Rust this is a null terminated string, a null terminated array. And yes, you can have a 5 terminated array if you felt the need to in the language. But the nice thing is whenever I build these, it makes sure that there is a null in the pointer. And the buffer doesn't overflow. So, we'll do the same thing. I'll keep talking though. Just as a brief thing with Ada, I never got it to work. I kept running into, so there's an Ada Core Technologies that has this free version of the tool chain, and I kept running into the edges of where they want me to pay them lots of money. It probably would have worked okay, but it was not worth it, because nobody actually is going to care about it. So we get these, don't worry about why my logging looks different. That's a configuration thing. All right, so Ada would be a lot of work. So there's no walkthrough for that one, but I left the slide in there in case I did get it to work. So the question is, what if we want to do more than hello world, which is a distinct possibility. So the biggest frustration in Zephyr, the APIs, well, they're not usually functions. We like static inline functions. We have macros. Most of our syscalls are macros that, depending on how you configure it, might be in a static inline. They might just call a function. They might do something that's a syscall. Some solutions, we can write wrappers. That's the easiest way to get going, is you just wrap around it. And on most of these targets, it's actually not that expensive. But it gets kind of awkward. And, there's mismatches between the languages. So Zephyr is written in C, and that mindset is kind of pervasive through the language. So there's a lot of work to be done here if this is something people want, but it's doable. As you can see, we can do logging. We can call hello world. I have a slide about logging, some stuff about syscalls and the complexity there. And I mentioned Zig's C interface, that it can just call these things, but that doesn't work right now, and I don't know how helpful that would be. And I just wanted to point out there's this other project called Zephyr Rust, which if you have to go pick a very specific version of Zephyr, a very specific version of the entire Rust tool chain, and it's basically patches to the standard library in Rust to make them natively work in Zephyr. And at that point you have it's almost like having a POSIX OS at that point. And again, it's a lot of work to get it working because you need very specific versions of the tools. So where do we go from here? It basically is, how much interest is there? Do people want this? And what level should this be something the Zephyr project cares about? Because there's definitely decisions. If we started and got something in CI that just builds a small Rust program, then people are going to notice anytime they change something that affects that. So at that point, it's not really a question I can just answer myself. That starts to be, it's a community project. What is the community interest? But no, we don't expect rewrite it in Rust. It's still a C project. Go use TalkOS if you want an RTOS that's written in Rust. All right, that's all I have. I think we have a minute or two for questions, so go ahead.
So let's imagine that you want to use like a Zephyr work queue in Rust.
Right.
Are you imagining right now you have to make a C wrapper for all the API around that?
It depends. So work queues you probably could just call. It gets kind of funny as to, well, was that a syscall in Rust or in Zephyr, or is it just a function call? If it's a function, you can just call it from within Zephyr. The callbacks, you can just write those in Rust. You can declare a function as extern C, and it's kind of like C++, and now this function, you can pass a pointer to it, to your work queue, so that it just calls it. And I forgot to read the question, yeah.
So my question's on similar lines. I'm living in some previous decade and I've never written Rust, so I don't know how much this is the case, but like, in order for you to call Zephyr APIs from Rust, does that involve making all of the safe stuff that you're doing using Rust unsafe? Or is there some way to solve that with like macros or code gen or something, like quarantine the unsafe parts?
So the question is, when we start calling C code from Zephyr, does that make all the unsafe stuff go out of the way? Well, turns out to call a C function, you have to say unsafe. It's a declaration in Rust. This code is not safe. Trust me, I know what I'm doing. It's basically what you're saying there. Usually, what you do is the tradition in Zephyr is to have, or in Rust, is to have one crate that is just wrappers on the declarations of all the C functions, and then to have another crate that defines a Rust type API that calls those but makes sure everything is safe. And that would, if we want to do Rust, it would be making that kind of library. So here's the Zephyr API like it would be in Rust, and then we can just use it and it's safe.
So it's kind of like Zephyr stubs?
Kind of. I mean, that's not the term they use, but yeah. Yes.
Yeah, I mean, one of the great benefits there is the send sync type trace, right? And Zephyr threads. I mean, how can I see a path forward?
So the question is, how does Rust's concurrency concepts translate into Rust? And why am I mixing these two up? How do they translate into Zephyr? So there's actually a pretty close translation there. I mean, the mechanisms, Rust is quite separate of the idea of sync and send. It has these attributes on types as to whether these things are type safe. You could either implement like mutex around Zephyr's mechanism or just wrap it a bit, but it's it's definitely code that has to be written in Rust to present a Rust type safe, Rust thread safe view of these data structures. But done correctly, then you would have that Rust safety of, well, this isn't protected with a mutex, I can't use it with Zephyr. I have not done any of this yet, so there's some questions as, is it going to be happy with a mutex that lives on the stack? Kind of questions, what is Zephyr going to think about that, or do we have to have some mechanism around that? So, yeah, I think we have time for one more.
Your demo with Zig was neat. I saw that you sort of put it in the same category as V and NIM and that new crop of C-lights. And you said your answer is already maybe sort of maybe, but do you know if it has sort of governance and stability and kind of structure like that? I looked it up. It has a software foundation that seems to consist of one company. Do you know if that's...
You're talking about Zig specifically. So the question is about what's Zig like as far as a project. Well, it's not a big thing like organized quite like Zephyr is. As far as I know, it's basically one person that kind of drives the development of it. So it's a big unknown where it's going to go and what it's going to be. It gets a lot of talk on Hacker News. So yes. So yeah, the question is, what about drivers in Zephyr in Rust? Sure. You have the wrapping stuff to do. Now you have to do it in both directions. You have the calls the driver needs to make, and then you have the thing above the driver. But I mean, they do it in Linux. It's not, you know, the question is, how much overhead do we end up with each driver that we add? And can that be shared if we have 5 drivers that are written in Rust? But that is another way to get Rust into Zephyr by contributing a driver that's written in Rust. Yeah.
Could you kind of confuse Zephyr, the kernel, with Rust pals that are popping up like these in order to have,
Yeah. So that's a really interesting question. It's about, you know, Rust has got a lot of HALs that are appearing. Not a real good correlation of the mapping between how those HALs work with what Zephyr's expecting out of a HAL, but it's something to consider. So, and I think we're getting kind of pressed on time here, but thank you everyone for attending.